Thank you for the introduction, and welcome to the last talk in the virtualization flavors session, where I hope you'll get a taste of virtual networking. So this is work that I did with my colleague from TU Berlin, Saad Hermak, Gabor Retvari from the Budapest University of Technology and Economics, and Stefan Schmid from the University of Vienna. So virtual networks in multi-tenant clouds are typically created using a piece of software that's running in the host OS called virtual switches. And these virtual switches are programmed to connect the different VMs on a server as well as across servers so that the different tenants appear to have a network under their control. Isolation between the different VMs is enforced at the virtual switch by configuring it with flow rules or forwarding rules, as well as a tunneling protocol like VXLAN for connectivity and isolation across the servers. And so in the past 10 years, there have been about more than 20 vSwitches out there. And most of the designs have been or have emphasized programmability or performance. And so for my research, it was interesting to look at the security aspects of these systems. And so we've actually uncovered quite a few security weaknesses of virtual switches. So let's look at the first one, which is the fact that virtual switches directly process untrusted data. So a malicious VM can actually send packets to the vSwitch that it would process. Next, we have the fact that the vSwitch as a component is privileged. So the packet parsing, which is quite a large attack surface, it happens either in the kernel or, if running in user space, is running with root or as sudo. Next, we have the fact that virtual network configuration is actually quite complex. And so the vSwitch there's just one vSwitch on the host, and that can be a single point of failure. So if you have a misconfiguration on the vSwitch, that could lead to a security misconfiguration issue. And so you could have one tenant's traffic leak into another tenant's. And finally, the most important is the fact that the vSwitch is oftentimes co-located with the host OS. And so an attacker, if she can compromise the vSwitch, actually can break out of isolation and also spread as a worm, as we demonstrated with Open vSwitch, where there was a buffer overflow vulnerability in the MPLS packet parsing that we could exploit to not only break out of the VM, but also spread across a data center, for example, like OpenStack. And we could show within about a couple of minutes, you can take down about 100 servers. So this work, or the paper at ATC, actually talks about how we can prevent or address those security weaknesses, which I'll talk about next. And then we look at what a performance evaluation. And then something that's not in the paper is how we can scale this system. And then I'll talk about some of the pros and cons and then conclude. All right, so if you've been wondering what MTS stands for, it stands for Multi-Tenant Switch. We actually had some discussion on what to call this. It was initially called MSwitch, but that was taken. And so we changed it. And so MTS is actually based on secure design principles meant to address all those security weaknesses. So the first one is a least privileged virtual switch, which addresses the problem of co-locating the vSwitch with the host. And so we move the vSwitch out of the host and into a virtual machine. And so even if the vSwitch VM is compromised, the host is not. And to address the point of, or to address the single point of failure, we have the least common mechanism. So we create multiple vSwitch VMs. And so even if one vSwitch VM is compromised, the compromised tenants are restricted to that specific tenant's VM. This also has the benefit of reducing tenant-specific virtual network configuration. Next, to add an extra security boundary, we run the vSwitch in user space. So for example, running OVS with DPDK. And finally, we have what's called complete mediation. So to connect all these different vSwitch VMs and the tenant VMs, we use what's called a single root IO virtualization network card, in short, SRIOV. And this implements a simple Ethernet switch or bridge in the network card that also supports VLAN tagging. And you can think of this switch in the NIC having ports in SRIOV called virtual functions that you can attach to the different VMs. And to isolate the different, say, tenants, so like over here, the red and blue, you can configure all those ports or VMs with a specific VLAN tag, so you have isolation at the layer 2. And so putting all this together, we compared this with the baseline, so running, for example, Open vSwitch in the host OS versus our solution. And for the SRIOV network card, we used a Mellanox ConnectX-4 NIC. And like I mentioned, for the vSwitch or the virtual switch, we used Open vSwitch. To run that in user space, we use OVS with DPDK. And we ran a bunch of standard VMs using QEMU and KVM. There were several factors that we had to consider for the evaluation, but over here, I'm just going to talk about 2 of them. The first is how we allocated resources. In particular, we had a couple of ways of doing this, and we'd like to just emphasize the shared resource mode, where we have the host OS pinned to a single core. So in case of running the baseline, we had OVS running in the host, and that was pinned to a physical core. And then we had our system, MTS, with 1 or more vSwitch VMs. And all those VMs were pinned to a dedicated core, apart from the host OS. The tenant VMs got their own cores. So the reason for that was so that the tenant VMs wouldn't actually be a bottleneck in our evaluation. Which brings me to the traffic pattern. So we had 3 typical patterns over here. The P2P, which is pure software switching. The P2V, so the packet goes all the way up to the VM in this case. And then we have the V2V, which kind of emulates some kind of service function chain. So it would go to like for our firewall and then to the actual host, for example. OK, so with this kind of resource mode and traffic patterns, we actually we made several measurements. And I'd just like to share the results from the throughput measurements. The first being raw packet processing performance. And over here, we have 64-byte UDP packets being sent. And we measured how fast the systems could actually forward those packets. And so you have on the x-axis the 3 different traffic patterns, so the P2P, P2V, and V2V. And on the y-axis, we have the forwarded throughput. And you have 3 clusters over here. And the dark gray bar is our baseline, as you can see over there. And then the green is a single vSwitch VM, and the orange when we have 2 vSwitch VMs, and the blue is when we have 4. And so you can see in the P2P, the throughput of our system compared to baseline is roughly the same. But when we look at the P2V, we can see that MTS actually has about double the throughput of the baseline, even though we've kind of added extra layers of security, which was quite a cool result for us. And when we thought about it, the reason for this improvement is because all the packets now go through the PCIe bus rather than through software. And so essentially, we've increased security for maybe a single core, but we've also increased performance, which is really cool. So this is just packet processing, but when we look at network applications as well, we see something similar. So again, we don't have a 2x increase, but about 1.5 to 2. And we can see that, again, with Apache and Memcached. OK, so The key takeaway, like I mentioned, is that for an extra physical core, we could get up to 4 times network isolation and about 1.5 to 2x increase in throughput. So this was just running like 4 vSwitch VMs, but in a real cloud, we'd probably want to run many more vSwitches. So we started playing around with running vSwitch containers in these VMs. And so far, we've been able to successfully run 12 vSwitches spread across 4 VMs. There seems to be some issue with QEMU and attaching about more than 36 VFs to VMs. And so we were hoping we could run at least 16 vSwitch containers spread across 4 VMs, but there seems to be an issue with that. We still have to evaluate the performance of this. OK, which brings me to the pros and cons. Of course, everything is not always pretty. There are some downsides to this. The first being, or primarily because of the fact that we use SRIOV. And by using SRIOV, since all packets now go through the PCIe bus, that could become a bottleneck, right? And when we go about like 40 gigs or 100 gigs, this could be an issue. But we haven't evaluated that yet. Second is the fact that the number of VFs on the NICs are limited. And so that could potentially be an issue when scaling. And if you want to do live migration with VFs, there's currently no clean solution for that yet. However, the benefits of this solution, I think, are really cool, especially when you think about serverless, where you want to be able to accurately charge customers for tenant-specific, say, virtual networking, which wasn't really possible when you have the vSwitch running in the host. And it also brings in the possibility to now run different vSwitches for different tenants. So if someone wants to run a specific software switch that has some feature that's not supported by OVS, you can now do that. You could also reduce the attack surface by, for example, reducing the packet parsing logic of the different vSwitches in the different tenants. And so with that, I'd like to conclude. And I think the key takeaways over here are that there are several vSwitches out there that have security weaknesses. And our solution, MTS, which is based on secure design principles, addresses those weaknesses. And when combined with SRIOV, not only increases the security, but also the performance for a modest increase in resources. All the scripts, data, and VMs that we used for this evaluation are on GitHub. So please check it out. That's it.
Thank you.
Hi, Anton Burtsev, University of California, Irvine. So I'm just curious, so what happens if you find a buffer overflow inside the network firmware, network card firmware?
Yeah, so in our threat model, the network card is part of the TCB. So of course, since our solution relies on trusting the network card, if that's exploited, the system can be exploited.
So, but in tangible terms, so do you believe the complexity of the code running on the network card is the same as Open vSwitch? I mean, you just moved it to a different hardware. Did something else happen?
So we got a similar comment in our reviews as well. I'm not sure if that was you, but
I'm not sure either.
I mean, so at least the way I understand it is that anyway, the network card is part of the TCB in the cloud. So whether there is a bug that can be exploited or not, it can be exploited, of course. So we just say, you're already trusting your NIC firmware. I mean, adding the simple layer 2 bridge into the network card with the SRIOV is, in our opinion, not going to change much.
Thank you.
Hi, I'm Harshit Gupta from Georgia Tech. Do you have any thoughts about how this would increase the cost of the provider? Because now there is a CPU constantly polling and it might even hurt the lifetime of that CPU core?
So that's a good question, and I think like using DPDK, for example, it's not only constantly polling, you have now your energy prices going up. So at least the results that I shared right now, maybe I didn't explicitly state that, was without using OVS with DPDK. So this was not running it in user space, just running it in a VM. Our results actually showed that it is, yeah, it depends. Yeah, but it's quite expensive to use DPDK because you also have to pay a price in resources then, which maybe doesn't work out.
Thank you. Great work.
Thanks.
I have a quick question. Is there a quantitative way to say how much you improve security?
Yeah, I mean, so measuring the increase in security is, I think it's always like firmware? Including firmware. Yeah, it's really hard. I'd love to do that. I mean, people say, okay, let's count the number of lines of code, and then you can say, okay, we've reduced the TCP in this way. I don't know, actually. Like, the way we've done it is mainly argumentative, but I would be interested to think about it a little more to have some kind of quantitative way of measuring this. Yeah.
Thank you. Let's thank the speaker again and all the other speakers in the session.